For most of engineering history, designers were forced to make a really tough compromise, a trade-off that basically put a ceiling on what was possible. But what if a material could just break the rules? Today, we're diving into the story of PEEK, an absolutely incredible polymer that solved a decades-old problem and, really, it unleashed a whole new era of innovation.
For generations, the choice was pretty simple, but man, was it frustrating. If you needed something really strong, really rigid, you had to go with metal. But if you needed something lightweight and easy to shape, you picked plastic. The problem? You could almost never get the best of both worlds. It was always a trade-off. And that right there, that was the core conflict. See, engineers didn't just want a slightly better metal or a slightly stronger plastic. They needed a whole new category of material, one that didn't force them to pick their poison between these critical properties. They needed to find a way to break the rules of material science itself. So to really get why this was such a huge deal, we've got to appreciate just how, impossible the demand for this new material actually was. Okay, just look at this list for a second. This isn't just a wish list. It's practically a list of contradictions. Materials that are strong are usually heavy. Things that can handle intense heat often turn brittle. And something that's resistant to chemicals, well, it might not handle being stressed over and over again. Finding one material that could do all of this at once was, for a long time, just a pipe dream.
And this need for an impossible material, it became incredibly urgent as technology just took off, pushing all the traditional materials we had right past their breaking point. After World War II, the world just sped up. Jet engines in aerospace were getting hotter and faster. Medical tools needed to survive being blasted with high-temperature steam over and over again for sterilization. And in all these critical fields, the old reliable materials were starting to fail in very predictable and very dangerous ways. So metals, for all their strength, they have an Achilles heel. You've probably experienced this yourself. If you've ever bent the little tab on a soda can back and forth, you know what happens, right? After just a few wiggles, it snaps clean off. Well, that weakening from repeated stress, that's called fatigue. And yeah, the concept is simple, but its effects can be absolutely catastrophic. Think about it. In an aircraft wing or a surgical tool, you just can't have a component suddenly snap after a few thousand uses. Reliability is everything. Now, engineering plastics, they had their own problem, something called creep. Imagine hanging a really heavy toolbox from a plastic hook in your garage. If you come back a year later, you might find that the hook has stretched out and is permanently deformed. It didn't break, but it sure isn't the same shape anymore. This slow, permanent bending was a huge issue. You can't have a gear or a bearing or especially a medical implant slowly changing its shape over its lifetime. You need it to be totally stable. And for a lot of plastics, that just wasn't happening when they were put under constant stress. So the crucial point here is that by the 1970s, this wasn't just some academic problem you'd read about in a textbook. In aerospace, in medicine, in the energy sector, engineers were hitting a wall. Material limitations were causing critical failures, and just making things a little bit better wasn't going to cut it anymore. And this is where the story takes a fascinating turn. Instead of just waiting around to stumble upon a better material, scientists decided to build one, from the atoms up. This was a completely revolutionary shift in thinking. Polymer scientists started acting like molecular architects. They stopped asking, okay, what materials do we have to work with? And started asking, what kind of molecular structure do we need to build to solve this exact problem? And the answer they came up with was this brilliant molecular balancing act. First, they used these stiff aromatic rings to create a super strong backbone, kind of like the steel beams in a skyscraper. Then, they added flexible ether links to act like joints, which kept the whole structure from becoming too rigid and brittle. And finally, they threw in these really stable ketone groups to basically shield the entire chain from chemical attacks from things like acids or steam. The result of all that intentional design was PEEK, or polyether ether ketone. Its very name is literally the blueprint of its molecular parts. It wasn't too stiff, it wasn't too soft. It was a material designed from its very core to survive just about anything you could throw at it. So once PEEK was out in the world, the old rules just didn't apply anymore. For engineers working in the most demanding fields you can imagine, entire design constraints, they just vanished. The change was truly fundamental. Before, designers had to constantly work around the weaknesses of their materials. But after PEEK, They could design for pure performance, knowing they finally had a material that could actually keep up with their wildest ambitions.
And this just unleashed a wave of breakthroughs. In aerospace, replacing metal became a real possibility, which led to lighter, more fuel-efficient aircraft without ever sacrificing safety. In medicine, implants and surgical tools could now be made from PEEK, which meant they could survive countless steam sterilization cycles without degrading, a huge deal for patient safety. That painful choice was finally over.
Now, to be clear, PEEK didn't replace every plastic or every metal out there. Its purpose was way more specific, and you could argue far more important. It was brought in for those critical, high-stakes applications, inside a jet engine or inside the human body, where the cost of failure was just too high to even think about. So PEEK was born from this incredible need to overcome the limits of strength versus weight. As we look to the future, you just have to wonder, right? What's the next great compromise in engineering that's holding us back? And what will the material that finally solves it even look like?